Hi guys, welcome to video 4. We're still continuing studying limits. You've been doing a lot of limits from at certain values from maybe the left and the right or just in general. Today we're going to do limits as they approach infinity. So we're talking about numbers for x that get really, really big or numbers for x that get really, really big but negative or small. We're also going to talk about horizontal asymptotes because those actually refer to limits as they approach infinities, and then we'll include vertical there as well. So first, we're just going to find a very basic limit. We're going to see what happens with this graph. Of course, when you're doing limits, the very first thing you should do is always plug it in. So I've got 1 over 2 minus 2, which is 1 over 0. And you should remember that when you have 1 over 0, there's no way that you're going to get that to reduce. That is always going to be a vertical asymptote. And so this is undefined or the limit does not exist. If you look at the graph really quick, we have a vertical asymptote at x equals 2 because x can never be 2. It's not a whole, it doesn't reduce. If I plugged in some values like x equals 3, I end up with 1 over 1. So I would have the point here. If I plugged in 4 for x, I get 1 half. So this graph ends up looking something like this. And I could do the same thing on the other side, end up with something like this. So I could talk about the limit as x approaches 2 from either side, just to kind of preview and show you this. So I'll just call this f of x. So instead of having to write the whole thing, I can just write f of x. See how that's nice? Okay, so if I want to do this one as x approaches 2 from the right, it doesn't actually flatten out to a value, but sometimes we will say that it approaches infinity. Technically, there's still no limit. The infinity just lets us know which way the graph is headed. The limit as x approaches 2 from the left or from the negative set of numbers is going down towards negative infinity. Again, technically the limit doesn't exist, but the negative infinity lets us know where it's headed. Okay, so let's look at a graph that actually does want us to find the limit as it approaches negative infinity. Okay, so in general, again, we've got a rational graph. We want to look at what happens as I plug in numbers for x that are really, really small. So big, negative. And we want to see if this flattens out to a value. Just a little flashback. You did this in Algebra 2 and pre-calculus. You might have said something like, as x approaches negative infinity, f of x approaches blank. And you might have called this end behavior. Technically, end behavior is limits for either infinity or negative infinity. You just didn't describe it as that yet, or maybe some of your teachers did, but now we're going to get more exact. So, okay, there are two ways to do this. One, you learn some rules for end behavior or limits to infinity in Algebra 2, and it had to do with this portion of the fraction. We're going to do it a little more in-depth way, but you'll see how those rules ended up coming into play. So for us, what we're going to do is we're actually going to divide each term or each part of the rational function by the largest power of x that we see. So in this case, the highest power on x is x squared. So I'm going to end up dividing each part of this limit statement by x squared. So like I'm going to put 2x squared over x squared. I'm going to put the negative 5 over x squared. I've got a large fraction. Okay, and by the rules of limits, we said we can find the limit of each part separately because I'm allowed to do the limit separately for subtraction, for addition, and even for division. So that's what I'm going to do. So I'm going to lose my limit statement because I'm actually plugging in or thinking about it as it approaches negative infinity. So in this first part, the x squares would cancel, which means x actually doesn't even play a role. It's constant too. If I plug in an infinitely negative, large negative number here, remember, I would square it, which would make it positive. And then you have 5 divided by a very, very, very large value. That's basically 0 then. That's an important concept to keep in mind. If the power on the bottom is bigger, we're getting closer and closer to 0 if we plug in something very small or very large. And again, by very small, I mean a very big negative. Here, my x squares would cancel and give me a 3. Because the power is bigger on the bottom here, the bottom gets bigger, which goes to 0. And again, bottom's bigger, 0. So the limit actually does flatten out always to 2/3. In Algebra 2, you learned if your powers, the highest powers were the same on top and bottom, it was just the ratio of the coefficients. Let's find an example or do an example where we're finding vertical and horizontal asymptotes. Okay, so your vertical asymptotes are basically zeros of the denominator that don't cancel. If they do cancel, then that's actually a hole in your graph. So important to note the difference. So you always have to simplify first. Horizontal asymptotes are really just me looking at the limits as I'm approaching both positive infinity and negative infinity. So that's kind of what I'm looking at. Is there a value that it's flattening out to? Okay, so first let's simplify our function. So I'm going to simplify that by factoring the bottom out to x plus 3x minus 3. And then as you see, I can simplify the x plus 3's. So this graph simplifies to x minus 3. Now this thing that I canceled out doesn't go away. Remember that -3, which is what makes this a 0, is actually a hole in my graph, but it's not technically a vertical or horizontal asymptote. Okay, so let's look at the result. In our result, we do still have a 0 of the denominator, which you could probably tell what this is, but once we get a little bit more difficult, you're going to want to set these equal to 0. Obviously, x equals 3 would make my denominator 0 here. So that's my vertical asymptote. For my horizontal asymptote, I'm looking basically as if there's a limit as x approaches positive infinity and negative infinity. So this is really kind of what I'm considering here. Because my denominator is going to continue to get bigger and bigger and bigger, I have a higher power on the bottom. This is going to approach 0. So I have a horizontal asymptote of 0. All right, let's look at another example as x approaches infinity. So we're going to try to see what we can do to reduce this to be helpful. If I'm looking at this, if I want to look at the powers of the top and the bottom to kind of compare how I think this graph is going to act, again, as I'm getting infinitely large or infinitely small. So on the top, if I plug in numbers for x that are like, 1,000 or 1,000,000, that squared times 9 is going to be so much larger than this plus 2 that this plus 2 is basically really insignificant. So I can really think of this top, or what I am thinking of this top as, is just basically the square root of 9x squared, because that 2 isn't really going to affect it as I'm getting really big. So does that simplify? Absolutely. It becomes a 3x. But what I think you have to be careful of here is, remember, when I square something and then square root that, I'm actually going to end up with a value that's always positive because you squared it, right? And then you took the square root. So you have to be really careful because when you simplify this into 3x, if x was originally something negative, so like again, imagine I had a thousand. If I had 1,000 squared, times 9 square rooted, I would get, the square root of that ends up being, something that's positive. And then when I plug it in here, that's fine because I take 3 times 1,000, no big deal. If x was negative and then I squared it and then took the square root, I'm going to end up with something positive. But think about it. If you put that negative value in here for x, it would end up being negative here. So the way that we can keep that from being an issue is we can put an absolute value around this result, and then that will guarantee that it does come out to the same positive result. So whenever you simplify a square root with a squared, you really should include an absolute value around your new reduced version. It doesn't end up being a problem here, but I'll show you why it ends up being a problem if we did negative infinity. So let's get back to the problem. So we said the top can be reduced basically then to absolute value of 3x. And the bottom's largest is 4x. Again, we're talking about values for x that are like 1,000,000, right? And if you have a million times 4, the minus 3 doesn't really have any pull on that value. Okay, so what happens as these numbers get infinitely large? Again, if I plugged in something positive, I would just get 3x or 3 times whatever that is. And on the bottom, the same thing, the x's cancel. I end up with 3/4. Again, these are positive numbers, so the top stays positive, the bottom stays positive, done. What's interesting is if I took the same exact problem but looked at the limit as x approaches negative infinity. So let's take a moment. We obviously know by the work that we just did that this is going to reduce down to basically the limit as x approaches negative infinity of careful. This is where this is going to come into play. So now you can see why the absolute value is important. If I put in a negative infinity here, 3 times negative infinity is going to end up giving you a positive number on top, but that's only because of the absolute value. If I didn't have the absolute value here, you'd think this reduces to 3/4. But now, if you plugged a negative in here, you'd end up with a positive number on top, but a negative number on the bottom. And so you'd end up with like a positive 3 over a negative 4 when you reduce that. Because again, the negative down here would stay negative, but the negative that you plug in up here is going to become a positive. So see, this side actually approaches negative 3/4, whereas the positive version stayed positive. You're going to see that come up in some of the problem sets. So I want you to be ready for that. So just keep in mind, if you're ever reducing an x squared in a square root, you need to put an absolute value around that before you find the limit. That's it. You're going to try your problem set. You're going to come into some problems that are a little more difficult. You're probably going to come upon a couple that make you really think about what's happening as you're plugging those values in for infinity. So be ready with questions if you have them in class, and I'll do some extra problems when we get there. And good luck.